Okay, today we'll study how to design state machine by using state diagram. Okay, for state diagram, okay, maybe you already know that it contains a set of arc or arrow, okay, labels with transition expression or the input condition. Okay, when state diagram is constructed, the transition expression between the arc defining a particular state must cover all input combination. Okay, namely, for example, okay, assume this is state A, state B, state C, state D. Okay, if I write some condition that change from state A to state B with, for example, X and Y, and this one may be X prime and change A to D by condition X and Y prime. Okay, now let you check, okay, and the condition when apply input, okay, to the state machine. Okay, this state machine assume that have got two input and maybe some output, maybe Z1, Z0, something like that. Okay, now I let focus, okay, only input condition to make state change. Okay, because there are two input variable, so there are four, right, possible value of the input, namely 0, 0, 0, 1, 1, 0, and 1, 1. When clock tick and input x1 is 0, 0. So how about this condition? X is 0, y is 0, so it's false, right? It's 0. Okay, and when apply x is 0, 0, right? Now x prime, x is 0, so inverse of 0 is 1. Okay, this condition become 2, and x and y prime, when you apply 0, 0 for x and y, this condition become false. So you can note that, okay, when you apply, okay, one input combination into the system, they will have only one transition expression will become true, okay, other condition become false. So when clock tick, the state machine will change state, okay, in the direction that make transition expression become true. Okay, and let apply 0, 1. When apply 0, 1, this condition become false, right? This condition x is 0, y is 1, x is 0, so this condition become true, right? X prime when x is 0, so it's true at here. X and y prime 0 and 1 prime, so it's 0. So for this input also make this condition become true. That means when clock 3, the state machine will change from A to C, and when input is 1, 0, 1, 0, 1 and 0 is 0, 1 prime, x is 1, right, is 0, 1 and 0 prime, okay, this condition become true. Okay? That means when clock tick and input xy is 1 0, okay, the state will change from A to D. And next, if at clock tick input xy is 1 1, this condition become true, right? This is false, this is false. So when clock tick, the state will change from A to B, right? So you can note that for each input that apply into the system, when clock tick, okay, there is only one arc or one arrow, okay, that will get the input condition become true. Only one. Okay. So that mean the next state, when you apply something to check, for example, if you want to check that this state diagram is okay or not, okay, you have two things that you must check. The first one, for each input that you apply into the system, it must have the next state. Okay, that means when you apply one of these condition must be come true. That means when you sum or OR, right? For example, if this condition may become true, this may be false, this may be false, right? When you OR this condition, okay, the result must be 1, okay, always, okay, 1 0 0, right? When you OR this 1 or 0 or 0, true or false is true, right? So it was always true. That means if you take for example x and y or x prime or x and y prime, okay, the result must be 1, okay, always 1, because one of these, okay, must be 1, okay, for any input combination. Okay, and one more thing that you must check, the next state, okay, when you apply some input, okay, the next state must have only one next state, namely there is no input that can make uh, uh, two or more condition, okay, become true at the same time, okay, at the same time. That means it's impossible that this condition will be true and this condition will be true at the same time, right? So that means if this condition come true, another condition must be false. So how to check the condition? That means if you and this and this, the result must be 0, right? Okay, because there is any two conditions, okay, become true at the same time. That means if I make this condition and this condition, x prime and x and y prime, so it's 0, okay, or check this and this, x prime and x and y is 0, right? And this pair also, okay, x and y prime and x and y, this is also become 0. Okay, so you just take, right, you just take uh, all pair of the arcs. Okay, when you end transition expression, the result must be 0 for all pair. So if you check, for example, in this example, at state A, there are 4 arcs or 4 arrows. So you must select okay, 2 from 3, right? So it's 3 factorial, 2 factorial, 1 factorial, or 3, 2, 1, 2, 1. So it's become what, 3, right? Okay. So if for example, if there are 4, right? 4 arc, when you select 2 of them, the result will be 4 factorial, 2 factorial, 2 factorial is 4, 3, 2, 2 factorial, 2 factorial. So it's what, 6, right? Okay. So if the state have a lot of arcs, okay, you must check, okay, many pair, okay, and together to check that it must be 0. Okay, so if the state have many state, so you must check many times. Okay, it take time out. Anyway, so for my opinion, I think, okay, to check this, okay, it's very uh, uh, convenient, okay, to check if you convert it to state output table. Namely, if you write something like this, state for example A, B, C, D, right? And input maybe X, Y, maybe 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and you just check to find the next step. If you can complete this table, okay, to find, okay, every next step for every, every step, okay, for all input combination. So you can check, right? If there is some empty next step, that means it's not okay. Okay, it's not okay. Or if some state and some input condition, okay, have next step at the same at the same condition. For example, at state D and input x, y is 0. If next state, if you convert, right, from state diagram to state output table, if next step may be A and state C at the same place, it's not okay, right? Okay, so it's easy, okay, to check for uh, state output table. Okay, if there is some place empty, that means it's not okay. Okay, or there are 2 or more next step at the same place, it's not okay. Okay, so this 2 principle is called all inclusion and mutual exclusion. Okay. Namely, for all inclusion, uh, any state, okay, must have the next state for all possible input combination. That means for any input, it must have next state. Okay. And for mutual exclusion, any state must have only one next state for any one input combination. Namely, it's impossible to have two or more next state at the same state at the same input condition. Okay, so that mean when we check, okay, for any state, okay, the next state for each input condition must have, okay, next state and have only one next state. Okay. Okay, now let's see example 4. This example let you design a tail light, okay, controlling machine. Okay, now let's see for this car, okay, tail light, there's 1 2 3 4 5 6, okay, 6 lamp at the tail light. Okay, when clocked, okay, I want tail light show the output, okay, follow this input condition, namely turn left, okay, turn right, and hazard, okay, 3 input. If left input active, okay, the output will show something like this. Okay, show something like this. And if you turn right, okay, if input right active, the output will show something like this. And for hazard, okay, or emergency, show like this. Okay, now when you design, the first thing that you should do for the design state machine is to determine the state of the system. Okay, for this example, you can note that, okay, there are many patterns of the output, right? Memory, okay, no any lamp turn on, and one lamp, okay, is named LA, okay, lamp LA turn on, okay, L is left, right, and LA and LB turn on, LA, LB, LC turn on, and on the right, RA turn on, RA and RB turn on, RA, RB, RC turn on, and all output, okay, left and right turn on. So there are how many patterns? No any lamp turn on, one left, one left lamp turn on, 1 2 3, 1 2 3, and all of these turn on. So there are 8 patterns, right, of the output, 8 different pattern of the output. So the state of the system for this example, it should have also 8 pattern, right? Because one state can have for more machine, one state, okay, can have only one output, right? Because the output based on the state only. So for this example, the state of state machine should have a state. Okay, for this example, there are a state, namely the state that have no any output active. let's say state idle, state L1. Okay, one lamp, one output for the left hand side of the tail light active. Okay, L1. L2, two lamp active. L3, three lamp active. Okay, three output for the left hand side active. Similarly, for the right hand side, there are state R1, R2, and R3. State R1, only output RA active. At state R2, output RA and RB active. And state R3, output RA, RB, and RC active. And for LR3, okay, all output active. Okay, so now okay, you can determine okay the meaning for each step, and you know output for each step. Actually, for this step, if you do some state assignment, namely because there are 8 steps, so it needs 3 bits, right, to represent these 8 steps with different binary code. So, for example, if you use Q2, Q1, Q0, if you use Q2, Q1, Q0 as state variables, and if you assign 0, 0, 0 for state idle, 0, 0, 1 for L1, okay, something like this, 0, 1, 0 for L2, something like this. So you can you can write output equation for each output, okay, because there are 1, 2, 3, 4, 5, 6 output, right? So you must okay write 6 output equation. For example, if you want to write equation for output LC, so you may focus only on logic 1 output. For L3, for example, if output L3, sorry, if L3 its binary code is 0, 1, 1, so you can write that LC equal to Q2 prime and Q1 and Q0, and this one at state LR3, okay, LR3 if its code is 111, so then LC will be active when the value of Q2, Q1, and Q0 is 111. So the condition of Q2 and Q1 and Q0 must be true. So to state, right? And you combine these two conditions together, so you can get this output equation for LC. For another output also do the same method, okay, by consider logic 1 output, okay, and let's consider the binary code for the state, okay, that give logic 1 output. So you can write output equation. Anyway, for this step, if you don't know binary code for each state, if you still don't determine the state assignment for each state, so you maybe cannot complete the output equation. Anyway, you may write take a note, right? For example, LC will be active if at state L3 or LR3, something like this. Or LB will be active at state what? L2 or L3 or LR3, for example. And after you do state assignment, so you just replace the name of each state by its its state condition or state assignment that you apply for each state. So for this step, just take a note for each output that will be active when the state machine is on which state. Okay, and now that you write state diagram for this state machine. State idle, L1, L2, L3, R1, R2, R3, and LR3. From this problem, if input left active, it may be change from idle to L1, left active, right? Input left active. And when clock tick, change from L1 to L2. When clock tick, change from L2 to L3. When clock tick, change from L3 to idle. If input left still be active, so it's go to L1, clock tick go to L2, clock tick go to L3, and back to idle. The condition for L1 to L2 may be always 1, right? Always true. So you can mark 1, to show that it's always true. Similarly, for from state idle, if input write active, so it's go to R1, write active. When clock tick, go to R2. When clock tick, change to R3. When clock tick, back to idle. The condition is 1 on 1. Something like this. And if hazard, input hazard active, if hazard active, so it's go to LR3, right? And maybe back to idle. And if no any input active, so maybe input let me write with this one. Input left not active, right not active, and hazard not active. So it still be at state idle. So by using this idea, maybe you maybe write state diagram like this. When you write state diagram, you should check that it's correct or not, right? By using the principle of mutual inclusion and or inclusion to check. For example, at state idle, and because in this system there are 3 input, right? So you should check all input that here have got next state or not, and have only one next state or not. For example, what happened if input left and write active at the same time. This condition becomes true, right? And this condition becomes true also. That means there are two next steps at the same time. It's not okay, right? It's impossible. So what should you do? You should correct the input condition for each arrow. Namely, if you want to turn left, actually only input left must be active, right? Input right must be not active. Input hazard also must be not active. So you can write more detail of the condition. When you turn right also, right? You must write right active, left not active, and hazard be not active. For this one is left and right invert and hazard invert. Okay. Anyway, when you check again, if L left active, R active at the same time. So when you check, oh, this condition is false, this condition is false. So this condition also false. Okay, you must check. Okay, all arc that leaving from the idle state. Okay, that is there any condition come true or not? When LR active, okay, input left and right active at the same time. In this case, oh, no any transition expression active. That means there is no next state, right? For this condition. So what should you do? You can define next state for this case. Namely, maybe I add, okay, to this condition to change from idle to LR3. Okay, namely if left and right, okay, active at the same time. Okay, so when I modify the detail, so we get something like this. Left hazard prime, right prime. Right, okay, only input right active, hazard prime, left prime. And add the condition left and right active at the same time to this hazard or emergency condition. Okay, furthermore, if you someone maybe consider it's okay, but someone think if some emergency want to show the tail light, okay, all turn on and off, okay. At the same time, when for example, if you turn left and some accident occur, okay, you must wait. Based on this state, again, you must wait one clock tick, two clock tick, okay, before check input hazard, right? And then go to the state that show all left and right lamp turn on, right? And then back to state idle and go to LR3 again. So note you must wait for 1 and 2 clock tick, right? But someone may think for emergency it should go to maybe at this state it should maybe go to LR3 suddenly, okay? If hazard active. If not, okay, go to L2. Okay. At state L2 also, okay. If hazard active, it should go to LR3 suddenly. If not, okay, continue to L3. Okay, and at L3, okay, because when clock tick is go to idle suddenly, and idle is one, okay, of the pattern to show emergency, right? So it's need not to change L3 to L3. So similarly for turn right also, okay, you can add this condition answer and change this, sorry, change from this direction, R1, right, R1 to this hazard. When hazard active, if input hazard not active, continue to R2, R2 also, if input hazard active, go to R3. If not, and continue to R3. So yeah, you can modify the state again like this. And okay, if and you think this one is okay, so let's use this state again, okay, to continue the state machine design. Okay, the next step, okay, to continue the design, you must determine binary code for each state. Namely, you must do state assignment, and because the behavior of state change, you can note that, okay, it's idle go to L1, L1 to L2, L2 to L3, L3 to idle, something like this. Idle to R1, R1 to R2, R2 to R3, and idle. So you know that it change idle L1, L2, L3, right? So if you assign the state code for L1, L2, L3 by using gray code, namely only one bit different between these states. So it's maybe reduce number of logic gate, okay, for next state logic, if or something like that. So for the example, let's design by using this state assignment. At first, state idle. Let value of state variables Q2, Q1, Q0 is 0, 0, 0. For L1, L2, L3, okay, it's beginning with 0. Okay, and this is 0, 1, 1, 1, 1, 0. Gray code order. And for R1, R2, R3, okay, it's beginning with 1 and gray code order. Okay, and the left binary code is 1, 0, 0. Okay, so it's used for LR3. Okay, now you now at this step, okay, you know binary code, okay, for each state name. So if you back to this node, actually now you can complete output equation for, okay, the system, okay, for each output. Okay, namely, for example, for for output, for example, output LC is L3 or LR3, right? By using this state assignment, L3 is what? L3 is 0, 1, 0. So you can write the condition of state variable to show that now the machine is on state L3 by using this condition to check Q2 prime and Q1 and Q0 prime. Okay. If this condition become true, that means now the machine is on state L3. And if the condition 100 of Q2, Q1, Q0, Q2 and Q1 prime and Q0 prime become true, that means now the machine is on state LR3. So the output LC, then you can write output equation is LC equals Q2 prime and Q1 and Q0 prime plus or Q2 and Q1 prime and Q0 prime. For another output also, you can write output equation by using this method. Okay, and how about transition expression? To determine transition expression by using a state diagram, you must write out transition list. What is it? Actually, transition list just list, or just rearrange this state diagram by consider the leafing arc or the arrow for each state. For example, if you consider state idle, there are 1, 2, 3, 4, right? 4 leafing arc, 4 arrow, that leafing from state idle. So you just write this arrow to transition list, namely start from idle to idle, start from idle to idle, and the input condition or transition expression. You just write transition expression of input condition here. And for this arrow, from idle to L1, from idle to L1, and the condition is left and hand prime and right prime, this condition. So you just write start and end state and input condition for every arrow. Idle to R1, this condition. Idle change to R1 by this transition expression. So if you just do this for L1 also, consider 1, 2, right? 2 leafing arc from state L1. So you just write down beginning and end. Change from L1 to L2 by this input condition. L1 to Li3, okay, by this condition. Okay, for a state, you do this for every state. After that, you just note, okay, binary code for each state name. For this example, I just write near, okay, or near the name of the corresponding state. For example, state L is 0, 0, right? L1 is 0, 0, 1, okay? L2 is 0, 1, 1, okay? L3, 0, 1, 0, okay? R1 is 1, 0, 1, okay? And this one also, right? Idle is 0, 0, 0. L1 is 0, 0, 1, okay? LR3, 1, 0, 0, okay? And so on. When you complete transition list, okay, to list all transition, okay, by observe from the arc or the arrow, okay, in the state diagram, okay, list all of this. After that, now you can find transition expression for any Q star. Q star means the next value, okay, after Coptic, okay, for each state variable. For example, Q0 star, okay, if you want to find equation for Q0 star, okay, Q0 star equal something. If you okay, that you consider, okay, only logic 1 value of Q0 star. Q0 star will be 1 when the state change from idle to L1. When this condition become true, right? Or I can say that Q0 star will be 1 when the state change from 0, 0, 0 to 0, 0, 1 when this input become true, right? Namely, okay, Q0 star will be 1 when this condition become true. Q2 prime and Q1 prime and Q0 prime, right? If this condition become true, that means now the state machine is at state idle, right? Because this condition will be true just only when the value of Q2, Q1, Q0 is 0, 0, 0, and 0, 0 is idle state. Okay, and this input condition must be true also with Coptic. That means you want and this input condition, left and hazard prime and right prime. Okay. This is the first condition that can make Q0 star become true. Okay, how about this one? This one start from idle, right? And this input, if this input condition become true, okay, it will change from idle to this state, which Q0 star is 1. So you can write it as Q2 what? q2 prime and q1 prime and q0 prime and this input condition. Okay. How about this one? And this one is q2 prime and q1 prime and q0, right? This is one. And this input condition hazard prime. Okay. If this condition become true and this input become true, okay, you change to the state L2, which q0 star is 1, and the last one is this one. Okay, it change from this state, okay, to this state when this input become true. So you can write the condition of the state is q2 and q1 prime and q0 and this input condition for q0. So from this one, so you can write by using this condition. Okay, combine these four conditions all together. This or this or this or this, and after that we may reduce, okay, number of expression by using switching algebra. For the output, sorry, for q2 star, q1 star also, okay, you can consider logic 1 value of each state variable, okay, to determine transition expression for each state variable. Okay, so for example, for q1 star, right, this one is q2 prime and q1 prime and q0 and hazard prime, and then or this one or q2 prime and q1 and q0 and hazard prime, or this one q2 and q1 prime and q0 and hazard prime, and this one 111, okay, q2 and q1 and q0 and hazard prime. After that, using switching algebra to reduce, okay, number of term and variable for q1 star. Note, okay, note, please take a note. If you use gray code, okay, for L1, L2, L3, something like that, because the input condition is the same, right? Hazard prime, hazard prime. Okay, so that means when you select this one, Q1, right? One here, 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 here. Note, okay, this input condition is hazard prime, right? Same, right? The same. And if the node state, okay, this state is called different only one bit. Different only one bit, right? That means you can reduce, okay, number of variable in the expression. That means when you combine this and this together, the result will be q2 prime and q0, right? Q0 is 1, and then hazard prime. Okay, you can reduce, okay, number of variable in the expression. Or this one also, this and this, right? No, it's two bit different. Okay, this one and this one, okay, it's one bit different, right? This So you can combine and reduce, okay, a number of variables. So by the result, okay, you can reduce them to this one. Okay. You can reduce, okay, if you use breakcode, okay. And for Q2 also, if you observe, right, or using logic 1, okay, you can get, okay, the transition expression for Q2 star, okay, like this, okay. And then using Boolean or switching algebra 2, minimize, okay, the expression. Okay, after that, okay, now you get the transition expression, right? That means, that means now for the structure of state machine, next state logic F, and now for this example, 3 flip-flop, right? And output logic G. Okay, for now, you can determine output equation. So you can write down circuit diagram for circuit G. And for F, you must know, right, relationship between output of F and input of F. The input of F in this case is there are left, right, left, right hand side, right, and feedback from flip-flop Q2, Q1, Q0. For transition expression, it shows relationship between output of flip-flop, right? Q2 star, something like that. Q1 star, right? And Q0 star, okay? Relate with the input of F, this. Okay. If you use D flip-flop, as state memory, okay? So, for example, this one is Q2, right? If you want Q2 star is 1, okay, you apply 1 at D, right? If you want Q2 star is 0, you must apply 0 at here, right? That means D and Q star is the same. So if you use D flip-flop, that means you can write down excitation equation, okay, by using the same equation of transition equation, right? Same expression. So that means your excitation equation for D2 then is what? Is this one, right? D2. And D1 then is this. D0 is this one, okay, this expression. So now you know excitation equation, right? That means now you can write circuit diagram of next state logic F. Then that's all, okay, for the design. Okay, I show you an example. For example, okay, for the previous lecture, I show you to design binary counter, right? by using input X, okay, to control count up or count down. Using this one. Last time, the design we use state, okay, output table at the beginning. But okay, that I show you how to design, okay, by using state diagram. Okay, at first, let me copy this one. Let me show you just for example. Okay, from this state diagram, let from this one, maybe we use 2-bit, right? 2-bit of this. Sorry, this one. Let's say Q1, Q0 for this bit and this bit, respectively. Okay, now state S0, change to S1, by the condition of X prime, right? X prime. Okay, then write this arrow, and this arrow is 1 to S2, right? S1 to S2. The condition is X prime, something like this. Okay, you just list all of this. Okay, now continue. S3 to S1, S2, S2 to S3, right? S2 to S3. The transition expression or input condition is X prime. And S3 to S0. S3 to S0 also, right? X prime. And S0 to S3. S0 to S3. The input condition is X. And what else? 3 to 2. S3 to S2. Input condition is X also. And S2 to S1. Input condition is X, right? And S1 to S0. Transition expression for this is X. So how many? 1, 2, should 8, right? 1, 2, 3, 4, okay, 8. And then for step assignment, okay, if I use D flip-flop for the design, flip-flop, maybe D1, Q1, and D0, Q0. If I, this is clock, okay. Now you must, okay, determine equation for circuit F and circuit G, right? For circuit G, the output is Y1, Y0. Okay, Y1, Y0. So if I assign state y1, okay, and q1 is the same value, y0, q0 is the same value. Namely, if I assign 0, 0, okay, for the state that give the output y0, y1, y0 is 0, 0. That means equation for G, okay, is y1 equal to q1 and y0 equal to q0. So it's easy, right? So that means now for state assignment, the value of q1, q0 then is what? 0, 0, right? Okay, let me take a note in here. q1, q0, and output y1, y0. For the state that output is 0, 0 is 0, 0. 0, 1 is 0, 1, 1, 0, 1, 0, and 1, 1 is 1, 1. Okay, the same. This is state S0, S1, S2, and S3. So you can write 0, 0 at here, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1. And it is S star, right? Next state, Q1 star, Q0 star. S1 is 0, 1, S2 is 1, 0, S3 is 1, 1, 0, 0, 4 is 0, 1, 1, 4 is 3, 1, 0, 4 is 2, 0, 1, 4 is 1, and 0, 0, 4 is 0. Okay, now I want to write down transit expression, right? First, for Q0 star. Q0 star is what? At this logic 1 is from state is 0, right? Or state 0, 0. So you can write it as Q1 prime and Q0 prime and X prime. Okay. This logic 1 is what? It's from 1, 0, right? So it's Q1 and Q0 prime and input condition is X prime. Okay. State condition and input condition. And this logic 1 output is 0, 0 and input condition is X. Q1 prime and Q0 prime and X. And this logic 1 is 10x plus Q1 Q0 prime and X. After that, okay, combine, right? This term, okay, to minimize number of variable and product term. Okay, you can combine this, right? Different one variable, right? This part is the same. So it's reduced to Q0 prime and X prime. And this term also, right? Different, only one bit. So it's Q0 prime and X. And then when you combine these two terms together, it becomes Q0 prime. Okay, this is an equation for Q0 star. And how about Q1 star? For Q1 star, is what? This logic 1 is from state 01. When called tick, this input condition become true, right? X is 0. So you can write as Q1 prime and Q0 and x prime. Next one is 1 0 x prime. Q1 and Q0 prime and x prime. This logic 1 is 0 x. Q1 prime and Q0 prime and x. Last one, this one, 1 1 x. Q1 and Q0 and x. Okay. Okay. Then now, okay, just combine these 4 product terms together, and then try to reduce the number of variable and product term. Maybe, for example, this one. Same, different, right? This one is same, right? And this is different, so it's XOR, right? Q1 XOR Q0. Q1 XOR Q0 and x prime. What about this? 0 0 1 1 x null, right? Q1 x null Q0 and x, and then from this group x prime, this group prime and x. So you can write it as Q1 XOR Q0 XOR x, right? Okay, so now you get equation of Q1 star, and if you use diff flop as the memory, okay, and the same expression, right, for D1 and for D0 also, namely D0 is Q0 prime. That means D0 is Q0 prime and D1 is XOR, right? For this, D1 is Q1 XOR, sorry, XOR Q0 XOR x. So from this state assignment, you know that y1 equal to q1, y0 equal to q0 as output equation. So your output is y1, y0, and your circuit F D1 excitation equation is D1 equal to this one, so XOR, right? XOR together. Maybe this is D1, sorry, this is X, okay? X, Q1, and maybe Q0 right here. XOR for excitation signal D1. And for this is Q0 prime, Q0 invert. Okay. Okay. Just for example, if you compare with this one, it's the same, right? Okay, if you use active low output, okay, you can draw this one. If there is some active low output, you can use this one. for diesel. Okay, so you get the same result, right? Okay, same result when you use D flip-flop, but it's not convenient. Okay, for using JK flip-flop or T flip-flop, if you use transition list, okay, to determine transition expression and then excitation expression, so this flip is convenient. Okay, so okay, just for example, okay, to design by using set diagram, okay, at the beginning. Okay, that's all for today.